Good day, everyone. My name is Amy Lambert. I'm EA's Director of Communications, and welcome to this webinar focused on environmental sequence stratigraphy. Now, I'd like to introduce today's speaker. Dr. Dan Walker is a senior geologist and practice lead for environmental sequence stratigraphy at EA. He has more than 36 years of experience as a sedimentologist and a stratigrapher. Dan?
All right, thank you, Amy. Thanks everybody for joining us. I'm going to be talking to you today about a concept, really kind of a bit of a paradigm shift in environmental science, referred to as environmental sequence stratigraphy. I apologize, obviously, in this kind of setting, I really never know what the technical level of the audience is. So I'm going to try to keep this very approachable for the non-geologist. But if I get carried away, which sometimes happens, just feel free to put something into the chat and we'll try to clarify it. What we're going to try to accomplish today is talk about the concept of environmental sequence stratigraphy, how it's typically addressed in industry now for contaminated site investigation and remediation. And then we're going to talk a little bit about what it's not. We're going to talk about the role of ESS in developing robust conceptual site models. And then we'll talk a little bit about what I think is kind of the unique take that EA has. Sorry, I just had somebody try to call me on my phone, on my watch. So what is environmental sequence stratigraphy and what it's not? I think the easiest way to do that is to kind of do it in reverse order. What it is not is just simply a rebranding of techniques that we've been using in the environmental field over the last few decades. It really represents a fundamental shift in how we try to incorporate geologic information to help us understand and identify, transmissive zones where the majority of contaminant may be occurring, and to therefore, reduce some of the cost and risk associated with site characterization and specifically remedial design and execution. So with that, Amy, why don't we go ahead and go to the next slide? So what we're really trying to do here is leverage an observation that's been made many times in the past. EPA just fairly recently in 2017, having gone through a lot of work reviewing many of their Superfund sites and RCRA sites, have recognized that many times the majority of the contaminant mass and the flux is contained in 10% of the media. So in other words, if we're dealing with largely unconsolidated media, which most contaminated sites tend to focus on, not exclusively certainly, but that's the majority of the sites that I personally work on. We're really trying to find those zones where the majority of the mass is, where majority of the water flows. And so it's really kind of an exploration exercise to try to identify those intervals in the subsurface where we're going to want to install monitoring wells or screened intervals, or a remedial design is going to incorporate an effort to focus on those highly transmissive zones where we're going to get the most bang for your buck. And really what that reflects is the fundamental concept that groundwater tends to follow the path of least resistance. So in geologic terms, what that means is we're looking for intervals where the hydraulic conductivity, the ability for rock to transmit water is the highest. So again, it's kind of an exploration technique where we're really trying to identify or mine those very transmissive zones. What we know from decades of work with groundwater is that those transmissive zones tend to be characterized by coarser material. If you looked at sediment under a microscope, or if you looked at some of this material under a microscope, what you would see is that the hydraulic conductivity really represents the porosity of that material, the void spaces between the individual grains, and then the permeability of that material, which is kind of the throats that connect those pore spaces. So because the pore spaces and the permeability are higher in coarser grained materials like gravel or coarser sand than say like in clay, what we recognize is that the majority of the contaminant is going to flow through those coarser intervals. So really what environmental sequence stratigraphy is a mechanism to try to understand the distribution of those coarser materials in our unconsolidated sediment that underlies a site. A couple things before I go too much further, just in case I slip into it. I spend most of my time working on PFAS contaminated sites. I do a lot of work around remedial investigations into feasibility studies and so forth. But that's really where most of my time is spent. So many times you may hear me, I'll just mention PFAS or something because that's actually the contaminant that I spend the most time on. And it's also the contaminant where we think ESS really has some additional power. Next, please. So what we're really, these coarser grained intervals, these transmissive zones are not randomly distributed. They really represent the way that the sediment was deposited early on. And so, hang on, I'm getting a bunch of pop-ups. So what we're trying to do here is utilize what we understand about geologic processes, about sedimentary processes, about the way that sediment is deposited to inform our strategy for looking at these highly conductive zones. And where this really, the initial power of it really comes to help us interpret what we see in individual boreholes across the site. And what we see many times is that the material changes in its character, the distribution of coarser material changes from borehole to borehole. That can present problems sometimes with our if we don't understand the context, that can present problems in terms of understanding how these data sets or these data points relate to each other. So in this example, which is from an LNAPL site, published in a report by Sadecki and Samuels, and we'll talk about them a little bit more later, what we see is because the material to the right was deposited very close to the source of sediment, it tends to be coarser grained, and then those coarser grained intervals become finer and thinner as you move away to the left-hand side of the slide. So the initial concept behind ESS was really to help us interpret this distribution and put it into a better context, which allows us then to do a better job of predicting pathways, which then leads to a more informed strategy for installing sampling techniques or putting in monitoring wells or injection wells, and what intervals we want to target in terms of like putting in a screen, for example. Next, please. So if you've been following some of the discussion, there's a lot of federal guidance out there about, how to do conceptual site models, how to do remedial investigations, the value of ESS. This paper on the left was published by EPA in 2017. Very good foundational study that talks about a lot of these principles. If you haven't seen it, I'd strongly recommend you take a look at it. But other entities, for example, the Navy has put out some fact sheets advocating the appropriate use of ESS and trying to educate people about how ESS fits in. And then we've gotten some fairly recent guidance from the Army Corps on the development of conceptual site models. That document, which came out in late 2023, doesn't discuss ESS by name, but many of the principles that are in that report are very relevant to the application of ESS. So they didn't go quite so far as to actually call for ESS in these investigations, but if you go through that work, you'll see a lot of components that are basically best informed through an environmental sequence stratigraphy approach. Next, please. You can go ahead and skip this one. We're just going to talk about this one in a little bit more depth. One of the things that I want to point out here is that environmental sequence stratigraphy is really about developing a testable, robust conceptual site model. And that development of that conceptual site model needs to really begin at a very early stage. And it can be informed, it's almost like a desktop approach. What you want to do is collect as much information that's already publicly available by the site, not just previous investigations, not just previous contractor reports or scientific investigations, but the more complete understanding of the site and in a geologic context. And so that's what's really key here. And I think this is where ESS can be very powerful. One of the things that I point out is, and I've seen this time and time again with various efforts, is when the contractor, any contractor, just relies on the most recent contractor report, whether it was an SI done a few years ago, or maybe it was a remedial study that was done for a contaminant 10 or 15 years ago, which is often the case, those reports often are not robust in the sense that they don't incorporate the broader information that's available maybe through the state or the county. And that's what's really key. And so this particular aspect of the Army Corps guidance is to really discourage people from cut and paste, their words, not mine, where you just simply lift the geologic information from a previous study and then just use that to inform your conceptual site model, add some site-specific data, and then you think you're off and running. That's really not the best way to approach conceptual site model development at all, much less through an environmental sequence stratigraphy approach. Next, please. So what does that mean in practice? All right. So this is a slide we put together, a figure we put together for a proposal. Don't need to get into the specifics other than it was located on the Front Range in Colorado as part of the Denver Basin. This is the typical approach that we take at EA to put a conceptual site model together at the proposal stage. Significant literature review, and by significant, I'm talking about a 15 or 20 hour effort by someone like myself, utilizing data sources that are publicly available. In this case, we incorporated the information from some previous studies, some geotechnical work that had been done out in the area. We added to that the information from the SI, but then we also had a conversation with the Colorado Survey, who had done a major review of the work of the aquifer, the Denver Basin aquifer, as a part of a larger effort to protect aquifers. And so in the upper left corner, what you see is a stratigraphic section developed with from a number of wells in the area. That was really insightful in terms of understanding how that geology was organized. The yellow areas are the more transmissive areas that were identified in that study, and that informed our understanding of what was going on at the site. It was a tremendous lift above just working with, for example, the SI data. The other thing that we did here was we incorporated climate information. As you can imagine, in the West, very, arid areas or semi-arid areas are prone to drought. What we see is a significant change in the water table, depending on whether it's, we're getting a lot of seasonal runoff or we're getting a lot of pumping. So we try to put the complete conceptual model together before we even start collecting data at the site. And that's what informs our strategy to what we want to propose, and it also informs kind of our risk calculations. Next, please. So if that was the model that came out of a proposal, the next stage is, okay, well, what are we learning at the site during, for example, a remedial investigation? This particular site, which is in the upper Midwest, is along a margin of what was a glacial lake, Wisconsin, a large glacial lake. As a consequence, fluctuations in the lake level kind of determine the nature and the distribution of some of these coarser intervals. So, for example, when the lake level would fall, streams would bring coarser sediment out into that depression, and you wind up with a coarser grain interval that's more transmissive. So this was informed by taking a conceptual site model that was very similar to what I just presented, and then we augmented that with geophysical data and geologic descriptions that kind of validated the model so that we had greater confidence that the site here was a fairly straightforward site, fairly layer cake geology as we would describe it. And so that gave us much greater confidence in the recommendations we were making for location of monitoring wells or screened intervals, et cetera. So that's kind of the process that we think works best. Next, please. All right, so let's kind of peel the onion a little bit and really talk about it. Basically, these two slides represent two different interpretations of a single interval. All right, we have geophysical data that tells us something about hydraulic conductivity and so forth. And then we have well locations and screened intervals where we have some descriptions, some geologic descriptions. But the point here is that if all you have is the typical information that's collected during a remedial investigation, and you don't have some prior understanding of what the geology is and what the types of depositional environments that are represented in this material, the way the material is actually deposited, for example, is it a stream deposit or a lake deposit, et cetera, you can come up with a non-unique interpretation. The first interpretation in the upper left just assumes that, you know, these are horizontal layers, they correlate from well to well. You know, that's the interpretation. Once we understand what the actual setting was, and we know that this is actually a set of point bar complexes, probably in a pro-delta environment, so where a river is entering a major water body, what we see is that those coarse grain intervals represented in the yellow actually are inclined. This isn't some kind of structural dip. This is the actual original topography represented as these deposits moved out and then basically fell down a slope. And each of those deposits is separated by what's referred to as a clay drape. So instead of being horizontal and continuous, they're actually somewhat discontinuous. And so if we pump material from one of these chambers, we're not necessarily in communication with the other chambers. And so as a consequence, we would get, you know, we might get results that are inconsistent and are difficult to interpret when we look at pump data or concentration gradient data or other types of data that we might be collecting. So that's why putting it in this stratigraphic context is such an important step. It reduces the risk. We're less likely to have to go out and drill additional holes. And that's really what this is about. Next, please. So just a little bit about the origin of sequence stratigraphy. Really started in the 70s and 80s. It was a major paradigm shift in the oil and gas industry, really driven by seismic exploration, especially in continental margin settings where we're talking about, you know, offshore reservoirs, where we're really trying to understand the large scale landscape. And so it really represented a fundamental shift. As a consequence, there's been decades of work that we can leverage to help us understand what's going on at individual sites in terms of process and how to interpret the data. I think the real key here is that to keep in mind is when you start talking about how to correlate from well to well, or you're trying to understand the three-dimensional distribution of conductivity, high conductivity zones or high transmissive zones in the subsurface, what we're really looking for is a way to understand or recreate that old land surface. What did the land surface look like at time A? How did that change to time B? That difference gives us some idea of, oh, the stream gravels have moved from one location to another, or there's been a big pulse of coarse material come into this setting. And once we understand that a little bit more thoroughly, the data begins to make more sense. And so what the real key here is that we're looking for a way to correlate from borehole to borehole where we see kind of a basin-wide response to something like a change in sea level or maybe a glacial retreat, something that's going to kind of affect the landscape more or less uniformly in a given time. And where this really comes into play in sequence stratigraphy, because it affects how the sediment is deposited, is the creation of something called accommodation space. Next, please. So if we were talking about, you know, a marine deposit on the outer continental shelf of North America, for example, that accommodation space, that area where sediment is going to tend to accumulate at an increased rate really reflects changes in sea level. These sea level curves are shown here. These are sometimes referred to as veil curves. They came out of Exxon production research in the 70s and 80s. I hate to say it, but I was actually around when these were being developed. And so what they do is it means that there was like a global change in sea level that then affected the basin more or less uniformly across its entire distribution. So as a consequence, the water got suddenly deeper almost everywhere. That affected the sediment that was being deposited there, and therefore that gives you something that you can trace, in some cases, over hundreds of miles. Next, please. But that's really being driven by what's referred to as this accommodation space, the creation of accommodation space. And you can create an accommodation space any number of different ways. If you have a mountain uplift, right, that's going to create more topographic relief. That's going to encourage coarser sediment to be eroded and then deposited into the basin. Okay, so that accommodation space in that case was tectonic. You can create accommodation space in glacial settings by an advance of a major glacier. That tends to push material up. It may depress the basin in front of it. It creates a volume that can be filled by coarser material. And because that occurs more or less uniformly in time across your site, it allows you to it creates a marker that you can correlate from well to well. Next, please. So what does this look like on the ground? Well, we're going to talk about a series of examples here in fluvial settings. These are, in this case, it's a meandering river or meandering stream. And at this scale now, think of yourself, you're on the riverbank, you're looking at this river. What you see is a series of depositional processes. Within the river channel itself, you've got rocks, boulders, different things, kind of, maybe not boulders, pebbles and gravel down the base of the river, in the river channel. Then as you go up the slope into what's referred to as a point bar complex, you get a series of finer and finer deposits. So if you look at this and pretend this is your well, you've got coarser material at the bottom, overlain by some very distinctive sandstones with very distinctive sedimentary structures like cross beds and so forth. That sediment tends to fine upwards until you get into this overbank material, which only sees deposition during the flood stage. All right. So what you wind up with is what's referred to as a fining upward sequence. We can identify these in wells, and we know that these fining upward sequences tend to correlate from well bore to well bore. So you're not trying to correlate individual beds so much as the overall trend. All right. So that's an important concept to keep in mind as we go forward. But the real key here is grain size is a really strong indicator, but to understand the system and understand how to make sense of that grain size trend, you also have to understand what were the processes that were responsible for the deposition of this sediment. All right, and we're going to talk about that a little bit more. Next, please. All right, so to do this, we're going to go to a meander belt. If you're in the Midwest, this isn't going to be news to you, but we know that, for example, PFAS sites oftentimes are associated with any location where there was a heavy management of or use of aviation fuel. AFFF, firefighting foam is a requirement when you deal with aviation fuel. You have to be able to train with that. You have to be able to monitor and manage your equipment. You have to be able to test your equipment. You may have to utilize that equipment and that AFFF, under real world settings. So every airport had an AFFF system. Most of the airports were originally built or originally sited on flat ground near a city. And a flat ground near a city in the Midwest oftentimes is in a floodplain. So in this particular floodplain, which is near Sioux City, what you see here is the Missouri River. It meanders back and forth between a couple big bluffs. These are the bluffs along here. The river migrates back and forth. And what you can see in this satellite image is a series of old oxbow lakes, old loops within the river, because as the river migrates through time, it deposits sediment in a very a complex manner. And it's understanding that complexity is the key to understanding how to identify and reconstruct that subsurface distribution of those transmissive zones. Next, please. So here's just a quick example. This is a meandering stream. This is actually a tidal stream near my home in Maine. Very typical. When we get into a meandering stream, what we kind of try to think about is, what's the current velocity within a meandering stream? And basically that's what's represented by the arrows. And in the terms of conservation of motion, when the water goes around the outer bend of a curve, it has to speed up to kind of maintain its connectivity to the rest of the water column. So as a consequence, even though the velocity is highest in that outer bend, that has a significant implication for the distribution of sediment. So for example, because the velocity is higher in the outer part of the bend, it tends to erode. That's why the bends get longer and thinner through time. The inner part of the bend is where the velocity is lower, so that's where coarser grained material tends to get deposited. There's very little fine grained deposition within the river channel itself as long as the water's flowing. So what we get then is when there's a flood and that water goes out over the top of the bank, out into the back bank, overbank areas, the velocity drops to zero, and that's when you get fine grained sediment. So we're creating a situation where you have coarser grained sediment on the outside, and then finer grained silts and clays as this kind of overbank deposit. Now, if this process continues through time, this loop is going to grow and grow and grow, and it's eventually going to create what we would refer to as an oxbow lake. Go ahead, next please. So here's a figure that I think shows some of the complexity. Here we have our channel again. We've got the coarser grain material deposited as point bar sediments. We've got the overbank, but we also have other little complexities like areas where the levee gets breached, and so you get a sudden pulse of coarser material out into the overbank. Or these oxbow lakes can become abandoned, and they just fill in and become very fine grained little intervals, even finer grain than some of the surrounding sediment. So in order to really make sense of the distribution of sediment and to bring this predictive power to the table, you have to understand where you are in this system. And that means, a little bit more analysis, a little bit more use of the information that we have, that we built up in that initial conceptual site model, and now we're looking to validate here at the individual site. Next, please. So as we mentioned before with these oxbows, the oxbow tends to grow through time. It's the interior portion of it. It tends to be very heavily dominated by coarser material as point bars. But at some point, the oxbow is actually cut off. And this cutoff then means that the majority of that river water is going to go in a straight line. The velocity within the channel begins to drop. And because that velocity drops, the channel begins to get plugged with really finer grained material, so that this then eventually just becomes an isolated lake. Once it gets to that point, the only deposition that's going to take place in that lake tends to be very fine grained clays. And so what you wind up with is a fairly complex setting with, predictable distribution of coarser grained material, going to be high conductivity material there, and then the lower conductivity, finer grained material. So it's actually a fairly complex setting. It's not a random distribution of coarser material. It's not a homogeneous distribution of material. It's actually a fairly anisotropic, setting, but we can interpret that information as long as we understand what we're dealing with. Next, please. So what does this mean in terms of fate and transport? Well, we're going to do a little modeling exercise here. These are actually runs that we did as part of a sensitivity analysis using ModFlow. That's a groundwater modeling package that was developed by the USGS, commonly used in industry to try to connect information and predict something about the distribution of contaminant plumes and their migration. In this simple example, we used a fairly common hydraulic conductivity, typical of silts and clays. We distributed that conductivity uniformly. And so what you get is, you know, if you release, in this case, let's say it's PFAS, it could be any contaminant that's not particularly dense or particularly light. So PFAS is a good candidate. It forms these long pencil thin plumes. The groundwater gradient is from left to right, so the groundwater is flowing left to right. So the shape of the plume and the density of the concentration within the plume is really just simply a function of that hydraulic conductivity. All right, but this is a very homogeneous system. It's not a real world system at all. If we go to the next logical step, can you go to the next one there, Amy? Thank you. Let's go back to our Oxbow Lake, right? We want to revisit this several times. What we have here is we've got this point bar complex that we talked about that's in the center part of the Oxbow. We've got channel fill material now. So this is that fine grained deposit that occurred once the channel was converted to a lake, all right? And then we have we're back into the silts and clays of the overbank, kind of the background setting. So as a consequence, the point bar, we're going to say, is coarse sand and gravel, very high hydraulic conductivity, very transmissive. We've got the fine-grained overbank or lake material, and then we've got overbank material. When we release our theoretical contaminant, the gradient is still running left to right. We let it run for 365 days, and then we run for 4,000 days. What you see is the plume is deflected significantly around this channel complex because the contaminant is outside this fine-grained barrier. So the point that we're trying to illustrate here is that, you know, when you have these complex systems, the plume is not going to behave in a straightforward manner. So we can utilize this information to inform our distribution of monitoring wells, the screened intervals that we might select within those wells. Obviously, you know, we're going to probably skew the distribution of monitoring wells, you know, to reflect this heterogeneity. In other words, we probably put more monitoring wells in the southern half of this site than we would just uniformly distribute them. Next, please. So that's just one example from one of many different kinds of depositional systems. In that particular case, it's a meandering river. It's part of the fluvial complex. Depositional systems represent, you know, the variety of the topography, the variety of the landscape. So they're going to range anywhere from like barrier island complexes to tidal flats to deltas out to dunes and alluvial fans. The majority of the sites that we work on really fall into two major categories. We have a number of three major categories. We have some marginal marine sediments, settings. We have a lot of fluvial settings. This is a very common process on the landscape if you're not near the ocean. And then a lot of glacial settings. As many of you may know, the northern third of the United States is heavily glaciated. That means that those glacial deposits, which are relatively young, make up the landscape that we've sited most of our infrastructure on. So we focus on those three major depositional settings, although you could have a site in any of these, but the basic principles work the same way. If you understand grain size, you understand sedimentary structures, you can begin to recreate a model of that three-dimensional volume that contaminant is flowing through. And that's the real key here. Next, please. So where is this going? Where's some opportunity for some improvements, how do you incorporate ESS into your portfolio, for example? There's several different aspects that we're exploring here at EA and that we're looking for collaborators moving out into the rest of the industry. But the first one is some kind of a decision tree process. When does ESS make sense? When do you get more value out of it? We find that it's very powerful on landscapes that PFAS is a perfect example where, you know, the contaminant has to be understood at very low concentrations. We want to try to identify the mass of that contaminant. We want to be able to treat that concentration, that concentrated mass first to kind of cut off the source, and then we can chase the down gradient plume. We think that we need to make sure that whatever additional work is done, it's justified in the cost. And we think that by reducing the risk, reducing the uncertainty early on in this process, we can reduce the overall cost of the project. What we're working on in terms of some new techniques is ways to incorporate more easily the wide range of publicly available data from our state surveys, from the USGS, from other sources, mining older remedial investigations to try to pull together as much information as possible early on in the project. That's a desktop heavy activity. And so, you know, it's perfectly designed for things like GIS, et cetera. We think we can do a better job of utilizing that broader set of data. And then we also want to find ways to improve the geologic descriptions that we're collecting at the site so that we can do environmental sequence stratigraphy in more effective ways. Next, please. So one of the things that we're spending a fair amount of time on here at EA is really trying to build up our GIS capabilities, make it easy for somebody that's working on a proposal or maybe a QOP, an early stage report in a report, to access data and pull it together. This is more than just going into the well records database. This is about pulling data sets from the USGS, from the state surveys, as I mentioned, and integrating them into a system that kind of follows the life of the project. Ideally, this information would be passed from stage to stage to stage. I would encourage you to encourage your support contractors to make sure that this information is easily passed to maybe a subsequent contractor or to the next phase of the project. I think we can generate a lot of additional benefit just by doing a better job of managing our data flow. Next, please. The other kind of tricky part of this is, you know, if you've been around these sites, you understand how the sites operate and how they work. We go out, we drill holes, we do borings, we collect material from the subsurface. A geologist describes that material, and then that material is disposed of. You basically get one bite at the geologic information that is represented by one borehole. We feel like every borehole is important, whether it's part of the SI, whether it's part of the remedial investigation, or whether it's part of a feasibility study or an actual remedial implementation project. And so what we want to do is we want to try to find inexpensive ways to collect and maintain geologic information across all of those stages. And we've become very enamored with the idea of using typical cell phone camera they actually are very powerful instruments. They have very high resolution. We are developing techniques to use those types of instruments, either a laptop, not a laptop, but a tablet or a cell phone, to collect these images, maintain those images, and actually use them to inform our interpretations. We think this is a very powerful opportunity here to break a problem, a chronic problem of how do you do QA/QC on geologic boring descriptions. You have a geologist there, they have one crack at describing it, and then that material is disposed of. Yet that material is integral to many of the interpretations we use on site. It provides tremendous context within which, if you invested in geophysical logging or other kinds of downhole data collection, it provides that geologic anchor so that you can do a better job of interpreting that geophysical signal in a geologic context. So we're very keen on expanding the use of digital cameras to capture and catalog this information. And this is something that's been done in the oil and gas industry again, in the mining industry. It's just something that we haven't utilized typically in environmental work, and it's something that I think is a very, very low-hanging fruit that we could go after. Next, please. So this is just kind of an example of this. This is from a boring in Minnesota, I'm sorry. And it just kind of illustrates the point. You've got a field geologist. They might be out there under any number of different conditions. If you've worked in the field, if you've done this work, you know that describing these borings and this material that we're spending money to recover and bring to the surface is just one of many responsibilities that the site geologist might have. They've got to coordinate with the drilling crews. They've got to work on other aspects of it. They've got some responsibility for health and safety. So this essential piece of geologic information that's reflects their professional judgment and description of this material as it comes out of a hole is just one of many things they have to do. And there's no way to do a QA/QC. That material is going to be disposed of unless we drill another hole within a few feet. There's really no way to go back and say, wow, let me look at that again. I'd like to look at this interval. I don't quite understand what's going on here. Many times this information is then taken and just put into a digital database, and the person that collected it is no longer involved in the project. And you've got a project geologist that now takes this information and tries to incorporate it into an improved conceptual site model. And it's just a real challenge in many cases. Most of the time, these in-field descriptions focus on something like Munsell color or the Unified Soil Classification Scheme. Those two are necessary, but not sufficient data sets to really understand what is the sediment, how did the sediment get deposited, how laterally continuous is it, does it really represent that transmissive zone that we're really trying to identify and go after? So that's where this incorporation of basically virtual boring records, where the sediment is, we take pictures of it with a high resolution camera, we incorporate that directly into the description. That provides us with not only an ability to somebody to go back and look at this material again, but it also gives us training opportunities. If we have a relatively young or less experienced geologist at a site, maybe it's the first time they're dealing with glacial sites, we can go in, we can talk to them, we can ask them questions, we can even do real-time conversations about what they're seeing as it's coming out of the ground, which improves sample selection, etc. So we think this is really a key to allow EA to bring, its expertise, its experience to bear on what's a fundamental aspect of geologic data collection, and that's these boring records. Next, please. So where are we going with all of this? I mean, basically, especially with a renewed emphasis on contaminants like PFAS, widespread problems, many different companies and entities working simultaneously. We know that industry is really trying to embrace the concepts of environmental sequence stratigraphy. How do we do that collectively so that we can share data among projects, we can share data among or share experiences across contractors and sites? We think that things like digital logging, digital geologic logging can be a real boost to that. We want to focus more on effective characterization techniques. We think this is really important. Things like electric conductivity or other high resolution techniques, geophysical techniques, for example, are really useful, but you need to put them in that geologic context, and environmental sequence stratigraphy is the way to do that. And then finally, as with many other aspects of kind of high resolution site characterization, what we see is that the initial cost, like for example, during site characterization may be higher. I would argue it's only marginally higher because we're using relatively inexpensive techniques. But that initial investment pays off down the road if you have a more robust conceptual site model. You're going to have a more effective remedial investigation, a more effective treatment feasibility study, more effective design opportunity with this additional data. That reduces risk, that reduces costs overall. These techniques that we've been talking about, like digital logging, et cetera, that just reduces the difference in the initial cost while maintaining additional value at the end. So that's why we're really excited about ESS. That's why we're excited about some of these emerging techniques. And that's what I'm hoping I was able to share with you today.